Assalamu alaikum. I welcome you all in the first lecture of Basic Mechanical Engineering Basic Mechanical Engineering course. Um, this is my introduction. My name is Sayyid Zadasri. I'm an assistant professor in Mechanical Engineering department at DHS Ufa University. These are my contact details. You can contact me via email using these email addresses. This is my office address. This is located at the main campus. So let's begin the course by discussing about the applications of mechanical engineering. Uh, Mechanical engineering is one of the most important and fundamental engineering disciplines right now. The application of mechanical engineering is very vast. You can see a mechanical engineering application all around you. It might start it the applications ranges from aviation, automotive, manufacturing, energy, power, you name it. Anything which is around you is has applica is can anything which is around you uh, can be attributed to the mechanical engineering. Here are some pictures where you can see the diverse application of mechanical engineering. In the first picture, you can see an air conditioning unit which is installed at the top of the roof, which is purely a mechanical engineering application. Mechanical engineering is used to design aircrafts, aeroplane, in aviation industry, in robots, in automation, manufacturing plants, in power sector or automobile or transportation industry, in energy sector or in utility sectors. So the application of mechanical engineering is very vast. And so further we will see the course outline of this course, which is basic mechanical engineering. The interesting part about this course outline is primarily this course covers the thermodynamic aspects of the mechanical engineering, whereas in reality mechanical engineering comprises of lots of disciplines which are thermal fluid sciences, design, solid mechanics of materials, structures, manufacturing, energy. But in this course, we will primarily be covering course topics from thermodynamics, energy, heat transfer, two-phase systems, and engines. So let me just read it out the main portion of the course outline, which are thermodynamic properties, energy and its conservation, energy and property relations, ideal gas, fundamentals of heat transfer, thermodynamic cycles, two-phase system, internal combustion engine, reciprocating compressors, introduction to air conditioning and refrigeration. So the detail of these topics can be seen on the right column. We will be covering all these topics in this course, and the sequence of the course the sequence of these topics might differ as we proceed with the course. So at the end of the lecture, at the end of the chapter, I will be providing you a guidelines that what topics are being covered in that particular chapter, or what topics are being covered till that chapter, or the videos we will be covering cover what part of the course outline, because some of the course topics in this course outlines are overlapping, and so it is it would be difficult for you guys to actually identify what topic has been covered and what topics are to be covered in the future. So I'm not going into the detail of these topics, but at the end of every lecture or every chapter, I will be communicating with you guys that this part of the particular which part of the course outlines are covered in that particular video lecture. The textbooks is Thermodynamics and Engineering Approach, 8th edition by Eunice H. Engel, Michael A. Bowles. I will upload this book on LMS, and I will notify you regarding the slides and the videos which I will be uploading during the whole course, right? So let's move further. This is the course assessment. 15% will be from your quizzes, 25% is your midterm exam, 10% is your assignments, and 50% will be your final exam. This course assessment division might change depending upon the circumstances which we might see in the near future regarding the COVID and other related stuff. Furthermore, let's begin our course formally. Chapter number 1, I will be teaching accordingly. This is the chapter number 1, introduction and some basic concepts. The objective of this chapter is to identify the vocabulary associated with thermodynamics, because as I mentioned earlier, the major part of this course is related to thermodynamics, so you should be well versed with the vocabulary associated with it. We will be reviewing some matrix SI systems, in which we measure different physical properties. We will be discussing some basic concepts of thermodynamics, which are system, state postulate, equilibrium, process, and cycle. We will be reviewing some concepts regarding temperature scales, and pressure gauges. So first of all, what is thermodynamics and what is energy? Thermodynamics can be defined as the science of energy. So what does it mean? Energy is a very the concept of energy is quite simple as far as the definition is concerned, but it is very difficult to explain energy in a line, right? So it is better to understand energy through different applications. So the study of the science or the study of energy is called thermodynamics, and energy is the ability to cause changes. You can, if somebody asks you what is the definition of energy, although this formal definition serves a purpose, but it is easier to understand energy from the different examples. For example, if you see that if a rock at the top of a mountain has some potential energy due to the height it attains, or it has the height of the mountain, but when you drop it, the potential energy converts into kinetic energy. So one form of energy is converted to another form of energy. For instance, if you have a fuel in your engine, you burn the fuel, and the engine works, and your car moves, which means that the chemical energy of the fuel converts to the mechanical energy, which runs the engine, and then ultimately it runs the car. So here the energy converts from one form to another. So basically, energy is anything which causes the changes, and thermodynamics is basically the study of that energy. The thermodynamics word is derived from Greek words therm and dynamics, where therm mean heat and dynamics mean power. Although in this course we will not be confining ourselves to study energy only in the form of heat energy, but we will be seeing work as well, kinetic energy, potential energy as well. So, but this terminology, thermodynamics, is being widely used for many years in this regard when we talk about energy sciences. So that is why we have adopted this word for so long time, for a long time. So do not mix it that in thermodynamics we will be discussing only heat, but rather we will be discussing different forms of energy. So moving further, this is some historical aspect of thermodynamics, some major events which occurred in the history. Steam engine, one of the most revolutionary devices ever produced by human being, was invented by Thomas Savery in 1697. The thermodynamics term was coined by Lord Kelvin, one of the big names in this field, in 1849, and later in the 1850s, first and second law of thermodynamics. We will be covering these laws in detail. Emerged primary output of the William Rankine, Rudolf Clausius, and Lord Kelvin. These are some big names which actually worked on these two laws, first law and second law of thermodynamics. And then later William Rankine published first thermodynamic textbooks in 1859. So this is a very limited history of thermodynamics. You can check the history of thermodynamics and major events in the history regarding energy and discovery of different forms of energies and conversion of one energy to another form of energy from lots of sources, books, and internet. So this is not as important. These are all facts and figures which are not as important to remember. So first of all, let's classify thermodynamics. We classify thermodynamics in two different. Classify thermodynamics. One thermodynamics is classical thermodynamics, and the other one is statistical thermodynamics. Classical thermodynamics is basically a macroscopic approach. Macroscopic approach means that in which we do not study the behavior of the system on a particle basis. Rather, see as a whole, right? Means that we do not run after each and every individual particle to study them, to study the motion or the different properties associated with it. Rather, we consider them as a system. On the contrary, we have statistical thermodynamics, in which we have microscopic approach, which is based upon the average behavior of large groups of individual particles, and in which this is rather a tedious job to do, because we have to consider each and every particle separately. The properties and different characteristics associated with the particles are considered on individual basis. So in this course, we will be covering classical thermodynamics, which is an easier approach and a direct and easy way to solve the problems. Moving further, importance of, first of all, what are dimensions and units. So firstly, we need to find what are physical quantities. Physical quantities are the quantity which are measurable. For instance, mass, length, volume, area, weight. All these are physical quantities which are measurable by any device, and they are characterized by dimensions. For example, if we say that one more thing, the physical quantities actually are defined by two main things. One is magnitude and one is unit. Means that if somebody has a mass of 20 kg, 20 the numerical value 20 is the magnitude, whereas kg is the unit. Usually there are fundamental dimensions. For example, for mass it is m, for length it is l, and for time it is t, and for temperature it is capital T. These are fundamental dimensions. What are fundamental dimensions? Fundamental dimensions, these concepts were actually covered in your intermediate classes. Fundamental dimensions are those dimensions which are not derived from any other dimension, whereas the secondary dimensions or derived dimensions are those quantities which are derived from these fundamental dimensions. For example, velocity is basically distance covered per unit time. So distance has the dimension of length, and per unit time and time has a dimension of small t. So v is not a primary dimension, it's a secondary dimension. And another example which we can take is volume, where volume is composed of three different lengths. So it's L by L by L, which means L cube, which actually is derived from a fundamental dimension length, and that's why, so it is L cube. L cube is the derived dimension. We can have another example. For instance, we can have let's say force is equals to ma, where m is the mass and a is the acceleration. The dimension of m is m, and acceleration is L upon t square, which makes it a derived dimension, since m, l, t square are all fundamental dimensions, and this is used in this derived dimensions. This is a table which is representing dimensions. For length it is meter, these are units. Mass is kilogram, time for second, temperature for Kelvin, electric current for ampere, and amount of light as candela. But usually in mechanical engineering we are more concerned with these top four: length, mass, time, and temperature. The bottom three are not as important as the top four. Moving further, there are two different types of measuring systems. One is metric systems and the other one is English system. Metric systems is widely used, whereas English system is adopted only by few countries right now. We will be using metric system in Pakistan. We use metric system. For example, the unit of mass in metric systems are kg. Length, meter is in length, and time is seconds. Whereas the unit of mass is slugs in English system. Feet in the unit of length is feet, and time is seconds. Usually we have some standard prefixes. For example, kilo means 1000, deca means 10, and if you're having a mega, it is exponential 3, giga exponential 9. For example, if I say 1 kilogram, which means that 1 gram is multiplied by 1000 is equals to 2 kilo, right? So these are the prefixes which we can use in different units, right? Moving further, This is the range which we in mechanical engineering, this is the range of the prefixes. For instance, this is the smallest range, which is exponential 12. This could be in any molecular level. This could be at a molecular level, and this one is at a for example, a power plant is producing energy at this rate, or this scale. Dimensional homogeneity, this is a really important thing. Dimensionally homogeneous means equation should be dimensionally homogeneous, which means that the dimension on the right hand side and left hand side should be homogeneous. For instance, if you remember the formula from your elementary classes, that S equals to VIT plus half AT square, where S is the length, of the as the dimension of S is length, and VIT plus half AT square. If you substitute the dimensions of all this VIT plus half AT square, you should get length L, capital L, on the right hand side as well. Otherwise it is not a dimensionally homogeneous equation. For instance, let's see example to understand the dimensional homogeneity. A school is paying $0.12 per kilowatt hour for electric power. To reduce its bill, the school installed the wind turbine with a rated power of 30 kilowatt. If the turbine operates 2200 hours per year at the rated power, determine the amount of electric power generated by the wind turbine and the money saved by the school per year. So what is happening here? There is a school which is paying some paying a bill at this rate, $0.12 dollars per kilowatt hour. What happens that in order to reduce the bill, they have installed a wind turbine which is making a power of 30 kilowatt hour. So they are running it for 2200 hours. So how much money they can save from by installing the wind turbine? So the total energy is basically can be found by the power, which is 30 kilowatt multiplied by time, because we know that power is equals to energy per unit time. So the power is 30 kilowatt hour, the kilowatt, and you are multiplying it with the time factor, so it's kilowatt hour. So this is 66,000 kilowatt hour is the amount of energy which is produced by this wind turbine over the course of 2200 hours. So now we have the rate for per kilowatt hour. This is a unit of electric energy. We are multiplying it and you get $7,920. This is the amount of money which you save. The basic concept behind this numerical is not to understand how the money and how the energy unit works. Rather, it is basically to understand that how to find the money, find the money saved for this. For example, for instance, if you have a unit which is $0.12 per kilowatt hour, you need to find dollars, and definitely in the denominator there is an energy unit over here. So you should be cancelling out this figure, this kilowatt hour, to obtain this dollar figure. In order to cancel a denominator, you should be multiplying it with a similar quantity. So in order to find you see that there is a power and you have hours. So if I multiply this kilowatt with hours, I can get this kilowatt hour, and by multiplying this fraction with the relevant number, which is here, I can find this. So even though you do not know the formula to find the money saved, you can use your knowledge of dimensional homogeneity, that the equation should be dimensionally homogeneous on right and left side. So you found the money saved. Another example we can see in order to understand the dimensional homogeneity is this example. For instance, you have a tank whose density which is filled with oil, whose density is 850 kilograms per meter cube. If the volume of the tank is 2 meter cube, determine the amount of mass. Although if you not most of you as in being an engineering or science students know the density formula, which is mass upon volume. But for example, consider someone who does not know the relation of density, which is the ratio of mass and volume. If somebody asks you to find the mass, so you know that density is over here and you have a volume, right? So if I cancel somehow this meter cube from the denominator, I can get the mass which is at the top. So here you have volume. If you multiply this volume with density, you can easily get the mass, right? So without even using the relation rho, you can easily find the amount of mass, and this is what happens here, density times V. but which is actually the real relation of density. But this is the importance of dimensional homogeneity. Even when you do not know how to, when you do not have the knowledge of the density relation, you can still find the mass in this case. If you have any question, if you have any query regarding all this which we have covered so far, you can please ask me in our live sessions, and note down your queries and questions. We will address them one by one. Moving further, let's talk about some unity conversion ratios. These are basic concepts which you might have covered in your elementary classes. For example, 1 Newton is equals to 1 kilogram meter per second square, because Newton is Newton is a unit of force which is represented by MA, and mass as a unit of kilogram, and acceleration as a unit of meter per second square. Another very important thing to understand, that in thermodynamics, usually a very simple arrangement which is called piston cylinder arrangement is frequently used in order to understand, in order to represent a system, in order to understand a system. So piston cylinder device is basically a cylinder with a piston on top of it and a gas filled in between the piston and the bottom of the cylinder. So what it does, you can since the gas can be compressed or can be expanded, because as you know that the matter has three major primary forms: solid, liquid and gas. So which means the gas can be compressed and expanded, whereas the solid and liquid cannot be compressed and expanded. So a piston cylinder device is a device which has a piston on top of it, and when you push it, it compresses the gas, and or when you expand it, it expands the gas. So you can actually move and changes the volume of the gas. So I will be using this terminology, piston cylinder, quite frequently in our next lectures and in future classes, inshallah. So moving further, let's talk about system and control volumes. First of all, what is system? System is a quantity of matter or a region in space chosen for study. Anything which is under observation is called system. For instance, if you have a number of molecules which are confined in a cylinder having a piston on top of it, these gas molecules are considered to be the system which is under consideration, and everything which is outside the system is called surroundings, and the surrounding and systems are separated by a boundary. That boundary can be moving boundary or could be a fixed boundary. In this figure, the moving boundary is the top of the piston, whereas on the walls and the bottoms are the fixed boundaries. So anything which is under observation, so because we will be considering, we will be solving we will be analyzing different problems, and we will consider them as system because we are considering them, and we are that is under observation. So for example, here we have system and this is boundary which is separating surroundings, but this is a general figure representation of a system, and on this one, this is a specific representation which is representing a piston cylinder device having a burner at the bottom. This burner is providing some energy to the system, and the gas is being heated. So this whole thing is a system, and outside, everything outside this device, which is piston cylinder device, is surrounding. There are two types of systems: open system and closed system. What are closed system? Closed system is a system which does not allow mass to enter or cross the boundary, for instance, but the energy can enter or energy can cross the boundary. For instance, this is a closed system where we have a gas inside. There is no mass transfer. You cannot add or take some mass out of it, but you can actually transfer some energy. The good example for the control closed system is, for instance, if you consider a can of cola, if it is sealed, you will see that if it is cold, after some time it will get hot, it will get heated if you place it in a room. So what it means that the energy from the room enters into the can and warm it, but at the meantime there is no mass transfer. Since it is sealed, you cannot add more cola into the can. This is an example of a closed system, and technically we call it control mass. Open systems are also called control volume systems. And open systems are those systems in which you can have mass transfer of mass as well. For instance, if you consider a water heater, which is commonly known as water geyser in your homes, in your houses, you have one inlet and one outlet. You have cold water entering from one end, and you have hot water leaving the system. So this system is not only having a transfer of mass in the form of water inlet and water outlet, but it is also having energy transfer as well, because you have a burner at the bottom and you are losing some energy from the side walls as well. So this is an example of a closed system, open system, which is also called control volume. In thermodynamics, there are lots of devices which are considered as open system. For example, compressors, turbine, and nozzles. We will be covering these topics briefly in our future lectures, inshallah. So the fundamental difference, I will repeat again, between the closed and open systems are: closed system does not allow any mass transfer in and out of the system, but it does allow the energy transfer. Whereas open system not only allows the mass transfer, but it also allows the energy transfer as well. So different examples and numericals will clarify what I'm talking about. Now let's stop here. This is in the next class we will see some more basic concept of thermodynamics, inshallah. So thank you very much for listening.